In this video tutorial, I would like to discuss the spring icon, which you can get in the Connections tab of the 3D Experience Release 2022x. Now, uh, the Connections tab appears in the modeling module, and you can see down here, here's the Connections tab. These are the options that you have, and here is rigid connection and spring. In this video, I would like to discuss the spring, and rigid connection will be done in a different video tutorial. It's an elementary discussion. We're not getting to the issues in depth, and I'll show you how to actually do the problem in a situation that you know what the answer is and you confirm it with 3D Experience. I want to remind you also that 3D Experience's FEA solver is the Abacus standard program. So there is some documentation, online documentation for the spring feature that I have a page of it here, and this is a more uh, detailed description of what it's doing. And of course, down here, you may want to pay attention to this thing later on if you try to do it yourself. The problem that we're going to be doing is a bar. We want to do it in the context of an example that is simple enough that there is a solution. So we have a simple bar. Think about it as 12 inches long, given cross section, and let's say that's made out of steel, although it really doesn't matter. What I would like to do is I would like to replace that 4 inch in the middle with a spring that has equivalent stiffness of this actual continuum 4 inch long steel bar. Okay, this end of the structure is clamped and the left end is subjected to 10,000 pounds. Now, when you use the icon that I showed you for spring, you get to choose two supports, and I'll show you what happens if I use these two faces as the support, and then you have to put the stiffness of this spring that you're making. Now, the stiffness is made in the elementary strength of material calculation. If you know the cross-section length, Young's modulus of each of these pieces. Each of these pieces are 4 inches long, and you plug it in the formula for stiffness AE over L, and you get 7.5 10 to the 6. So this particular piece on the right that we are actually modeling a continuum element has the same axial stiffness as the one in the middle and as the axial stiffness on the one on the left. But this is really what we need. We need the stiffness of this middle spring, which is AE over L, 7.5 10 to the 6. Now, uh, uh, just be aware of the fact that when it comes to calculating analytically what the tip deflection is here, you have three springs basically in series, three springs, the one on the right, the one on the left, the one on in the middle. Now these things, of course, we're going to be modeling the one on the right and the one on the left. But if you were to do this thing analytically, each of these will have a stiffness of AE over LK, and the uh, the effective stiffness of them being in series is 1/3 of that, K over 3. So if you put all those numbers in there and you put the load, the tip deflection is going to be 0.004 inches. So whatever we get, we're going to be comparing against this number. Now, when it comes to this particular modeling feature, you have choices between kinematic coupling type, continuum coupling type, and structural or structural distributing type. Okay. Now, when you do it with coupling, notice that you get pretty much the same thing that we got for deflection, at least 0.004 roughly. Here's the continuum coupling type, and this is the structural coupling type. You get the same deflection. And the stresses, although they look different, although for the case of continuum and structural, you have most of it is 10,000 psi as you're supposed to, but in the case of kinematic, at the juncture between that spring that we're going to make and these solid ends, there is some stress concentration, etc. But as soon as you go away, then it's okay. So this is kind of ruined where the connection is between the spring and hypothetical spring and the solids, but this one looks fine. Uh, just to let you know that the way it works when you create the spring between these two faces, basically things are spider elements are created between this node and this point and the other nodes. And later on, I'll show you what happens if I actually, instead of doing a spring between the face and face, I do between these points. And of course, if you go this route, the stiffness of each one of these springs is going to be 1/4 of the spring that we calculated, stiffness of the spring that we calculated before. What happens if you do it with a situation like this? Well, the deflections are going to be, obviously, this is not as stiff as the one that we did before between the faces, and that's why it deflects more. And of course, but the stresses are going to be obviously okay. The stresses are going to be constant stress. The blue stress is about 10,000 psi. There is some, you know, local disturbances here because of the presence of the spring. Okay, so I want to show you probably this at the end. All right, so let's go ahead and create our model. I already changed all my units so that they're in inches and psi and pounds. So let's see now. On this vertical plane, I will sketch my 1 inch by 1 inch square. So let's dimension this thing. This is 1 inch. And so is this one. 1 inch. Exit. And we're going to pad this thing for 4 inches. 4 inches. 4 inches. Okay, then I'm going to make a plane which is 4 inches away from that face, and then on it draw a rectangle and then pat it again. So the different ways of doing this, but this is how I'm going to do that. 4 inches away on this face, on this plane, I will sketch a rectangle that's 4 inches by 4 inches. Maybe the easier way is just to project this end on that plane. You can see that right there. Exit. When you project it, obviously the dimension is correct and you don't have to adjust it. So let's flip this thing and make it 4 inches. So these are the two pieces that we had to create. Now let's go and apply our materials. So tools, under create a material, I'll call it a spring video. Spring video. All right. Let's apply this to that part. And now we're going to input our values. We're assuming that's made of steel, 30 million psi, Young's modulus, and 0.3 Poisson's ratio. Okay, this is okay right there. Double click on it. Structures, abacus multiphysics, mechanical, elasticity for Young's modulus 30 million. 1, 2, 3, 4, 5, 6. And Poisson ratio 0.3. That's all we need. All right, now we're going to do the meshing. So we're going to go structural model. Uh, okay, so I will use tetrahedral mesh parabolic. Don't forget to select your geometry. This geometry is that part. And for mesh size, I will leave this thing like that and see how it looks like. So say okay. Yeah, and if you want to look at it, you just update it. There we are. Okay. So this is fine. Maybe it's a little bit yeah, it's a little bit finer than this mesh. So let me actually use slightly coarser mesh here. Let me see. So we go there and maybe I'll use 0.25. How about that? 0.25 mesh. That's fine. Okay. Now, uh, right here we have the connections tab. See that connections tab? As I told you that in the connections tab, you find the spring that we discussed earlier. Right there, there is the uh, spring, and this is the rigid connection in a different video. So we click on the spring. Now, a couple of things I'm going to do. First of all, if this is in your way, you can hide the mesh, but this is fine right now. So I'm going to go between this support, this face, okay, and for the support 2, I'll choose the other face, this face on that side, okay. Notice that it places a mesh here and it creates the spider that goes to all the nodes there. Okay, so it's an axial spring, and the uh, elasticity or the stiffness of it, it was 7.5 10 to the 6 7. So let's go ahead here, 7.5 e to the 6 lbf per inch. Now you can change the unit so that it actually becomes this, but I didn't do that. So notice that it did change it. If you go under what is that connection here, engineering connection, under spring, if you double click on it, you see that they changed it to that unit, kilogram per second square, but it's the same as 7.5 pound force per inch. Okay, that's pretty much it. All right, so we are done here. Now we're going to go to structural scenario creation. Let's select the finite element mesh that we created. All right. For procedures, we're going to do a static step. And although the problem is linear, fairly small strain, small displacement, I will leave this include geometric nonlinearity on. I'll leave it there. This is dummy time, so I will leave everything the way it is. So we say okay. Now we're going to go to the restraint. The restraint, that end is completely fixed. So clamp this face. Okay. And this end, this face is subjected to a force of 10,000 pounds. So we go to load. This is a force, 10,000 pound in the direction, that'll be X, 140 in the direction X. There we are. And that's pretty much it. So let's go ahead and run it. You see now we go to simulate. It's a good idea to do a model check, scenario check, and then run it, but I skipped the first two because I'm pretty sure it's going to run. There may be some warnings, but that's fine. Let's give it a minute. Once this runs, I will come back and replace that one face-to-face spring with 4 vertex-to-vertex springs at the corners, and then of course you have to assign 1/4 of the stiffness to each one of those end springs. And you'll see that the deformation is going to be much larger than what it's supposed to be, but it's doable. As I said, although it's going to give you wrong deflection. Okay, it's almost finished. Okay, so let's close this, close that. First of all, let's look at the deflection. It better be 0.04. Yeah, that's 0.004. That's fine. The numbers are a little bit different because the mesh that I had in the previous slides that I showed you, these meshes are a little bit different. They were coarser than what I had here. Okay. Now, if you want to look at the stress, there we are. Roughly, what the maximum stress is totally, I mean, you should ignore that because that happens at the corners of these. But right there is about 10,000. Put the cursor on it, get 10,000 psi. Okay. Now, okay. Now I want to show you what happens. Oh yeah. Now notice that if you go here, if you double click on this spring right there, if you double click on it, this gives you different types of coupling. So the one that I showed you, the one that you see here, was the continuum one. Let's do the kinematic one and run it. Remember, I showed you some stress distribution here. Okay, the one that I showed you was this is the kinematic one here, which is relatively close to what I've got here on the screen, except that this is a different mesh. Okay, this is a different mesh, and it's a finer mesh, so that's why it probably looks better than what you see in the other one. So did I change this thing to a kinematic? Yeah, I did change it. Now I have to run it. Not there. Scenario run. Let's give it some time. While this is thinking, uh, yeah, you see some irregularity. You will see some irregularities here instead of being nice and orange like that, and that's because of the fact that this is the interface between the spring and the face. That's why it looks like that. So you've got to be careful in the vicinity of the place that the spring creates those spiders. The stresses you are got to be very careful to literally take those as the values, because in real life you know that there is no such stress there, but because you're approximating the middle section with a spring, obviously something is going to give. And I'm not going to do it with the structural modeling. You can try it yourself. However, I will go and delete the spring in a minute and replace it with 4 springs with a stiffness 1/4 of what it is now. It's extracting the results. Okay, so you can see that there is some local deviation from uniform stress that is supposed to be there, but the numbers are, I mean, obviously these oranges, things like that, you should completely ignore. What is important are these the stress should be, yeah, the stress, there's something wrong here, we have to check this. Oh, sorry, this is not the last step. Let's go further. There, 1.28. The stress here is roughly 10,000 PS. So I was looking at a different increment. That's why it didn't look right. Good. And if you look at the deflection, it's going to be fine. The deflection is going to be just like what we had before. And again, this is at the last step. Be careful here. Last step. It's going to be 0.004. Okay, so what I'm going to do now is delete the spring. Let's go back here. We go to, let's go back to model. Okay, so we had this spring. I'm going to delete it. And I'm going to delete that connection right there that is created because of what we just did. Delete this. I'm going to replace it with four springs of 1/4 of the stiffness that we had. So let me see now. Let me hide this first of all. All right, so back to spring. The first one is going to be between this point and for the support 2 is that point, and you repeat this thing 4 times, and for that value you put 1/4 of the value of the stiffness that we had before, which is 1.875 instead of 7.5. Okay, e to the 6. Okay, so we go 1.875 e to the 6 lbf per inch. Let me see if I can do a copy here. Oh, copy. Okay, good. Okay, so that's the first one. Let's do another one. Going between this point, second support, that, oh, not the edge, not the edge, remove this corner. Yeah, and paste. Let's try it again. 1.875 e to the 6 lbf inch. Let me copy this. All right, one more. This, oh, the value, the value of it. Forgot to put the correct stiffness value. Paste. Yep. And the final one is on this side. And for the other support, that corner. Anything that's blocking your view, you can hide this and paste. Okay, everything else is the same, so we're going to go run it now. So let's go to scenario and run it. And I will leave it to you to look at the results and decide for yourself whether it's in agreement with what we had before or not. Anyway, I have some screen captures of the runs that I made earlier, but these are for a slightly different mesh, therefore the numbers are not quite the same. By the way, notice that when you do these point to point one, vertex to vertex one, you don't get that option of kinematic and continuum or structure anymore. But it's point to anything else, you'll get those options. And the description of the coupling type is you may have to look at the documentation, but it has to do with something with uh, how the averaging is done. Okay, it has to do with how degrees of freedom are calculated uh, in terms of something. That something being rotation. Okay, I suggest that you look at uh, the, the documentation of 3D experience or Abacus for that matter. The root of this goes back to uh, what is called coupling, which is also in the same connections tab, but the root of this goes back to REV2 or RBE2 and RBE3, which I have separate video tutorial on it, rigid bar element 2 and 3. That's where the root of this coupling type is. It'll be done in a minute, and you should get something that you can go. The deflection is going to be a lot bigger than what it's supposed to, because it's not as stiff as if you put springs basically between every point and every point. There we are. So almost 3 times uh, softer. And again, the reason that these numbers don't quite match with what I had in my video is the video segment or the slides, is that the mesh that I have here is a little bit different, maybe a lot coarser than what we had before, than what I had before. All right, good luck.